Crossed roller bearings. That's what we're talking about. They pack an extraordinary punch in a compact package, handling radial, axial, and moment loads simultaneously with unmatched rigidity. At least that's what I think makes them the go-to for design engineers that are tackling precision turntables, indexing systems, and heavy-duty machine tools. That's what my research tells me. But I thought I'd check in with Doug Martin, who is, in fact, a heavy-duty machinery engineer who's based in Vancouver and who has kindly agreed to help unpack the fundamentals of cross roller bearings with me. So why don't you get us started then by telling me what distinguishes a cross roller bearing from ball bearings or other roller types in terms of their design and performance?
Well, a crossed roller bearing is interesting in that when we when we look at a regular rolling element bearing, all the rollers are or balls are in line, and they're all each one is making the same effort as the one that precedes it or is after it. However, what's interesting about crossed roller bearings is that they are at an angle of 90 degrees to each other. So one roller has a certain job in one direction, and the other roller has a job in the other direction. And that gives one of its unique properties, or its properties, that we can have a single row bearing that is able to do a multitude of tasks all at the same time. In such, because it can do more than one job at one time, you can actually get a compactor design. You can squeeze it into a smaller space, and it still is effective in doing that job. What's in terms of the roller design itself, it's not quite, but it's also a perfect square, meaning it's got roughly the same width as the same outside diameter. And that's what's really interesting, is within the channel that it runs in, you have 4 races instead of just 2 races. And it's how these rollers interact with the 4 races that gives it these unique properties. Because of this, you're able to get, or as a part of this, you're able to get very good accuracy, both in the running accuracy of the bearing itself, but also in its ability to resist tipping moments. And this is where its special attributes, or these attributes, make it a choice for designers who need something that runs very, very accurately, but also something that's very stiff. Now, granted, it's not seen in everyday industrial applications to a large degree, but when you get into applications that need the special purposes, that's where you see it. In heavy industry, we do see it in large slewing ring bearings, and perhaps that it could be on tower cranes, it could be in excavators, where you may have some limited space, but you need the bearing to be able to smoothly run and do its multitude of tasks. But in the industry that's growing right now, specifically in robotics and also in semiconductor assembly, the machinery that's designed for these applications require very precise movements and very precise positioning of the work. So for an example, if you have a robot that has an arm that moves, you want that arm to be able to place the piece of work in an exact spot. And this is where, because of the precision of the crossed roller bearing and the moment resistance to moment tipping, it can actually do that task very, very effectively. In medical imaging equipment, you have a large bearing that has to be large enough to surround a person's body, so to speak, or that's where the machinery has to allow a person's body to go inside of it. So you've got a very large diameter bearing that's supporting the cameras and such, and they need to be very precise in their positioning, so that the radiologist or the doctor that's going to look at this equipment is going to get a good picture and good resolution of what they're looking at in the human body. I mean, even in applications like in security in airports, same goes for that, right? You've got these devices that your baggage goes through, and that the camera or the sensing device has to be mounted on a rotating frame, So as you can see, and these examples I'm giving are things that are new, that are new today, right? That are being developed now, or maybe in the last 10 or 20 years. We're not talking about equipment that was designed 100 years ago or such, like as in some of the heavy industry applications.
100%. So let's take that a little deeper dive into the robotics example. So in robotic arms, for example, or direct drive actuators, how do they, for example, enable short stroke, um, high acceleration moves? Talk me through that.
So, so when you have short stroke high acceleration, like what you're mentioning, what we may do is apply a preload to the bearing, or basically squish the rollers, or have the rollers um, with a preload such that you've taken the elasticity out of the assembly, meaning that as you're accelerating quickly and decelerating quickly, you're not getting any, or you're getting a reduced amount of, let's say, bending or elasticity within the assembly, which means you can make very quick movements very precisely, because you don't have to overcome um, any of the, or you overcome less deflection of the component as you're moving it and as you're moving it with the load. Does that make sense?
No, gotcha. Okay, that really helps me visualize a little bit more.
Well,
Talk.
sorry, and I apologize for interrupting, but it's just like in a machine tool. If anybody disassembles a machine tool spindle, they already know that, this is older practice. They already know that the bearings that support the machine tool spindle have a preload, so that when the grinding wheel pushes into the work, it doesn't move as much because there's no elasticity in the system.
So takes me to the next question, which is how do rigidity, accuracy, and repeatability influence application outcomes? This too, for me, relates back to more of the robotics or industrial applications.
It makes repeatability, right? That's really the bottom line, is that you have to make repetitive motions accurately, consistently, over a long period of time and repeatedly. So you're removing the variance in one rotation versus the next. So it's about targeting,
Okay.
making sure you hit the target each time.
I wonder if we can talk about trade-offs and what trade-offs exist for cost, for speed, for lubrication, service life. I know this is an area that you are very, very seasoned on.
Well, certainly with roller bearings, the roller bearings actually put more demand on the lubricant because they run warmer, and as such, they will degrade the lubricant faster. So, as long as you choose a proper lubricant for the temperatures that might be generated by the roller bearings, um, as well, a roller bearing versus a ball bearing, because it can be more weight to the rolling element. Um, you're going to need more torque, so that you're putting some more demand on the motor. The other thing in terms of new technology is that a ball bearing or a ball bearing assembly that may do a similar job, you may be able to get into ceramic rolling element, ceramic balls instead of steel balls, which therefore reduce the weight and give you more performance. The ability to make a ceramic cylindrical roller bearing or cylindrical roller is a little bit more tricky, because it's not a uniform all the way around form. So if you wanted to take an option of going to a ceramic roller, it would actually be a lot more cost prohibitive than if you were using a ball bearing in the same application. However, and it's on, we've had ceramic rollers in the mix for quite a few years. So it doesn't discount it. It just means that it may be more expensive, maybe a more expensive option.
So let's talk more specifically about crossed cylindrical roller slewing bearings and um, and the 4-point contact ball options. Um, how does the one outperform the other in stiffness and accuracy? But before you can do that, you need to define for me the difference between the two.
So again, with a cross roller bearing, it's quite simple. A single row of rollers at 90-degree angles. A 4-point slewing ring bearing can either be the way will have can have a single row of balls with a raceway that's ground with two different curvatures, right? One curvature for one direction, the other curvature for the other direction. The disadvantage of the ball bearing is that you cannot get it to the same accuracy. There's more elasticity because the ball is in contact at a point, and therefore the actual point load is greater for a ball than a roller, right? And therefore, if you have a higher load, you have more force trying to stretch the elastic, so to speak. But on the other hand, because you only have a point load, then you put less demand on the lubricant, or sorry, you turn the lubricant less, you roll over the lubricant less, and therefore the lubricant may last longer. However, we come back to that point that there's a higher point load at the spot, and therefore it could fatigue faster. The cross roller bearing again will spread the load out over a larger area, will reduce or will increase your fatigue life. But again, there's could be a little degradation of the lubricant. However, if we're talking about large slewing ring bearings, they tend to operate very slowly, and therefore they don't really have that much heat generation. So in that case, in either case, with whether it's the ball or the roller, you're really depending upon the additive package that's going into the grease that will protect the surface when there's no lube film separation. That's kind of a basic principle. The other side of the coin is it's much easier for a manufacturer to make a ball bearing race in a large slewing ring bearing than a cylindrical roller bearing race. So that's where there can be some cost advantage to the ball bearing type. And we have to remember that the induction heat, these slewing ring bearings are induction hardened, so you have to remember that the placement of the induction hardening tools as you do the final work on the bearing will matter on how the hardness on the raceway is developed. And because your contact area is longer on the roller, there might be some requirement to have space for the second pass of the pass of the induction tool on the second raceway. That might affect the geometry of where you have the roller contact. So that would be another thing that I would be thinking about or seeing as a difference between the cross roller bearings and the 4-point contact ball bearings.
Okay, thank you. So next I want to go to ask you a little bit more about targeted industries or applications for cross rollers. Where do they excel for multi-directional loads, for example?
Yeah. I think robotics and automation right now is the number one place for these items, because of course with robotics we want them to take up a small space, right? And as such, we want to have the thinnest cross section possible, right, to make a more efficient machine. And we're also not only taking up less space, but how can we do the job with a less mass? And as I said, and I kind of mentioned before, semiconductor manufacturing equipment. We hear about what's going on in the with the AI industry and the demand for semiconductors, right? It's probably one of the, in fact, there's anything that we hear, we're not making enough semiconductors to meet the demand for AI. So there's clearly a demand in general for these type of manufacturing equipment. But if we also think about how small these things are, right? So certainly in the manufacture and assembly of semiconductor equipment, there's not very much space whatsoever.
So let's talk about some of the specific SKF features and that you can talk to in helping to mitigate cage creep, for example, or help with lubrication issues. What are the specifics that you can talk about that would, I guess, extend the life of the bearing?
Well, certainly, if and I've got one prime example of someone that was using a larger diameter slewing bearing, and this can apply to whether it's cross roller or otherwise, is where you actually place the lubricant holes. And if we think about the application, it might be something that has a limited amount of rotation. So, in knowing what your arc of rotation is, you would certainly want to have lubricant entering the system at the key points. In other words, if we think about a bearing that does 360-degree rotation, you can add lubrication at one point and have that lubrication drawn all the way around the ring. But if you now have a ring that's only skewing back and forth 15 degrees, 30 degrees, even 90 degrees, if you expect that you're able to grease it in one spot and have the grease transmitted all the way around, you're probably not going to find good reliability with that. So, that's where you would certainly have to understand the number of lube inlets that you might have in the bearing, and either whether you should put them or specify or request that you have the lubrication going into the right places all the way around the ring to address the lubrication needs of the bearing.
Wonderful. Doug, this has been so enlightening for me. It's been a while since I went into the weeds on bearings like this, and I really enjoyed it. It brings me back to my old days of covering components proper. So I really appreciate your time today. Thank you so much.